In this lesson, you'll deal with one last application for the ideal gas law. It's known as partial pressure. And what I want to do first is just go through an introduction of what partial pressure is, and then we'll get into some of the examples. Basically, what partial pressure is just if you're given a container of gas, and let's say in that container you have two or more gases mixed together. This is just basically saying that the total pressure of that container is just the sum of each of the pressures of each of the individual gases. And it's known as Dalton's law of partial pressure. So just to give you a diagram of what Dalton's law of partial pressure is talking about. In this case, you have a gas in one container, which is at pressure 1. You have a gas in another container, which is at pressure 2. And then if you were to go and add those two together into a third container, the total pressure of that container would just be pressure 1 plus pressure 2. And just to go through a couple of points for the different calculations for partial pressure. Pressures do need to be in the same units. So let's say you have a pressure in torr and another pressure in atmospheres. You need to make sure that you get both of them, preferably to atmospheres, so that you're then able to do the calculation that you need to do. And with partial pressure, there are two different types of calculations that we're going to deal with, which I'll show you right now with two different examples. Alright, so this first example you can find in your note packet underneath partial pressure. Basically saying that you have a 10-liter flask and it contains 1.031 grams of O2 and also 0.572 grams of CO2, and that's all at 18 degrees Celsius. And what you're trying to do is figure out the total pressure. Now there are different ways of doing this, but probably the easiest way to do this is to take each of the gram amounts and just convert those both to moles. So the first one was 1.031 grams, and that was for O2. So just divide that by the molar mass of O2, which is 32, and you end up with 0.0322 moles. Then take the other one, which was the 0.572 grams of CO2, divide it by the molar mass of CO2, which is 44.01, and you end up with moles of 0.0130. Now if you were to go and add those two together, add those two mole amounts together, you would end up with 0.0452 moles. And just by knowing the total amount of moles, you can then go and find the total pressure of that particular container as well. And the way that you would do that, you would do it just like you would any other PV equals nRT equation. So for volume, it was 10 liters. For number of moles, you would take the total that you just figured out, so 0.0452 moles. R would just be 0.0821. Temperature would be the 18, but you have to add 273 to change it over to Kelvin, so you'd have 291 Kelvin. And you'd look for pressure in this case. Now the pressure that you would solve for, or you would eventually get, that would be the total pressure of the whole entire container because of the fact that you took the total number of moles. So put everything into PV equals nRT, solve for P, and you end up with a total pressure of 0.108 atmospheres. Now another way to do this would have been to do two separate PV equals nRT equations, or calculations I mean, using each of the mole amounts. Everything else would stay the same, like the temperature and the volume. Those two would stay the same, but it would be the number of moles that you'd actually be changing. That requires a little bit more work, so this one is a little bit easier to do. And for the second type of problem that you can have with partial pressure, and again this is in your note packet, in this case you're given a sample of O2. It's at a volume of 3.42 liters, and it's what's called collected over water, which we'll deal with in a second. You're at 25 degrees Celsius, and you're actually given a total pressure in this case of 1 atmosphere. You're also given the partial pressure of water is 24.5 torr, and you want to figure out the moles of O2. Now when it says that it's collected over water, it's just basically saying that you have a mixture of water vapor and also O2 within this particular container. So by having the total pressure of the container and by having the partial pressure of water, you are able to figure out the partial pressure of O2 from that. Once you find the partial pressure of O2, then you can figure out the moles of O2 using PV equals nRT, which we'll deal with in a second. Alright, so the first calculation that I have on here is just basically changing the 24.5 torr over to atmospheres first. So if you divide that by 760, you end up with 0.0322 atmospheres, and that's just basically the partial pressure of water vapor. Now, because of the fact that we have a total pressure of 1, and we just figured out the partial pressure in atmospheres of water vapor, we can then go and subtract those two in order to be able to get the partial pressure of O2. So the partial pressure in O2 in this case would be 0.968 atmospheres. Plug that into PV equals nRT. So pressure of oxygen is 0.968 atmospheres. The volume was 3.42 liters. We're looking for the number of moles. R is always 0.0821, and then the temperature is just 298 in this case. Plug that into PV equals nRT, solve for N, and we end up with 0.135 moles of O2. So that's just a different type of problem that you can have with partial pressure, where in this case we're given the total, and we just need to figure out some variable within PV equals nRT. And before we can actually go and do that, we do have to find the partial pressure of that other gas within that mixture. So what I want you to do now is just basically work on the partial pressure worksheet that I have posted for you in first class. Once you do that, then begin working on the Unit 5 review that I passed out, and just know that you do have a test coming up next Monday, February 6th.